Welcome to Tech Disruptions, deep dives into the technologies reshaping industries, from AI to quantum to biotech. Let's get into it.
So the term quantum supremacy has been floating around for a few years, conjuring images of supercomputers solving impossible problems. But it turns out even that definition is a moving target.
Absolutely. The goalpost has definitely shifted. What was considered a landmark achievement just a few years ago is now being reevaluated, largely thanks to new developments like Jupiter reaching a 50-qubit benchmark. It's not just about hitting a number, it's about what that number means in the broader context of computational power.
And the big reveal here is that this 50-qubit system isn't just a marginal improvement. It fundamentally redefines what is even called quantum supremacy, making previous claims almost seem quaint.
Precisely. It forces us to ask, what exactly are these machines being compared against? And are the right questions being asked about their practical capabilities? The race isn't just quantum versus classical anymore. It's quantum versus better classical algorithms and more powerful classical hardware.
To delve into that further, when Google's Sycamore processor hit 53 qubits and demonstrated quantum supremacy in 2019, it was hailed as this monumental breakthrough. The claim was it performed a specific computational task in 200 seconds that would take the fastest supercomputer 10,000 years. Now there is Jupiter at 50 qubits, and the conversation is completely different. What changed?
A lot has changed, primarily on the classical computing side. Remember, Google's claim was immediately challenged. IBM, for instance, argued that with better classical algorithms and more optimized use of existing supercomputers, that 10,000-year estimate could be brought down significantly to days or even hours for that specific task. The supremacy often hinges on the best classical alternative at the time of the quantum demonstration. What Jupiter highlights is that classical algorithms have continued to advance, often specifically tailored to mimic or even simulate the quantum circuits that were used for supremacy demonstrations.
So essentially, the classical world didn't just sit still. It saw the quantum challenge and optimized its own capabilities to narrow the gap. It's almost like a quantum computer sets a new high jump record, and then the classical engineers immediately invent a spring-loaded shoe to clear the same height.
That's a good analogy. It's a continuous arms race, really. The problem Google chose for Sycamore, a random circuit sampling task, was specifically designed to be hard for classical computers but relatively straightforward for a quantum processor. But once the nature of that problem was known, classical computer scientists could develop highly specialized algorithms and hardware architectures to tackle it more efficiently. Jupiter, by reaching 50 qubits and presenting its own benchmark, implicitly acknowledges this evolution. It's not just about the raw qubit count, but about the robustness of the quantum claim against increasingly sophisticated classical methods.
Let's clarify the distinction between quantum supremacy and quantum advantage. These terms get thrown around interchangeably, but they are not the same, are they?
They are absolutely not the same, and the shifting goalpost makes this distinction even more critical. Quantum supremacy, as originally conceived, means performing a computational task that is practically impossible for any classical computer, regardless of its architecture or algorithmic sophistication, within a reasonable time frame. It's a demonstration of raw computational power that classical machines simply can't match for that specific, often abstract problem.
So it's more about proving the existence of a different computational paradigm, rather than solving a useful problem.
Exactly. It's a scientific milestone, a proof of concept that quantum computers can do something classical computers can't. Quantum advantage, on the other hand, is about performing a useful computational task faster or more efficiently than the best classical algorithms on the best classical hardware. The key word there is useful. This is where the real-world impact lies, when a quantum computer can accelerate drug discovery, optimize logistics, or break encryption in a way that provides a tangible benefit.
And what Jupiter demonstrates with its 50 qubits is that even achieving supremacy has become harder because classical systems are so good. It's raising the bar for what impossible for classical even means.
It really is. The initial supremacy demonstrations were often based on problems carefully constructed to be hard for classical systems, but easy for quantum. These weren't necessarily problems with direct, immediate applications. The Jupyter benchmark, implicitly or explicitly, pushes the field towards problems where the quantum advantage isn't just about a niche academic task, but potentially something more relevant. It forces researchers to think more critically about the type of problem they are trying to solve to demonstrate this computational superiority.
So if 50 qubits isn't just a number, what does it signify beyond the raw count? Are all 50 qubits created equal? Because it is known there's a difference between physical qubits and logical qubits.
That's a crucial point. No, not all qubits are created equal. The number 50 refers to physical qubits. The actual computational power of a quantum computer isn't solely determined by the raw qubit count, but also by their quality, their coherence time, connectivity, and crucially, their error rates. These are noisy intermediate-scale quantum, or NISQ, devices. They are prone to errors, and that noise limits the depth of the quantum circuits you can run and the complexity of the problems you can solve.
So even with 50 physical qubits, if they're too noisy or don't stay coherent long enough, it's not truly possible to leverage all 50 in a complex calculation. It's like having a 50-car train where half the engines break down halfway through the journey.
Precisely. You might have 50 cars, but if only 10 or 20 are reliably pulling their weight for the entire duration of the trip, your effective power is much lower. For complex, real-world problems, what is truly needed are logical qubits. These are error-corrected qubits, built from many physical qubits working together to mitigate errors. A single logical qubit might require hundreds or even thousands of physical qubits to achieve a stable, error-free state. Jupyter's 50 physical qubits are still a significant engineering feat, demonstrating greater control and potentially better error rates than previous 50-qubit systems, but they are not yet logical qubits.
This distinction seems critical, as it provides a clearer understanding. The discussion is not about universal, fault-tolerant quantum computers yet. The field is still in the NISQ era, where every additional qubit is a battle against noise.
Exactly. And the Jupyter benchmark, by pushing the envelope with 50 physical qubits, helps understand the boundaries of what's possible in the NISQ era. It gives a clearer picture of the challenges in scaling these systems. It's not just about adding more physical qubits. It's about improving their quality to allow for deeper, more complex computations before noise renders the results useless. The fact that a 50-qubit system can still redefine the Supremacy benchmark suggests that the quantum community is getting better at squeezing more reliable computation out of noisy qubits, even if they aren't fully error-corrected logical qubits yet.
So if the classical side keeps improving its algorithms and hardware, and quantum systems are still battling noise, how does this impact the timeline for when truly useful quantum advantage might be seen in areas like drug discovery or materials science?
It means the timeline remains uncertain and highly dependent on breakthroughs in error correction. The shifting goalpost effectively raises the bar for what constitutes advantage. If classical computers can simulate quantum systems of increasing complexity, then the quantum systems need to become even more powerful, either by increasing qubit count dramatically and improving quality, or by achieving stable logical qubits. For complex applications like drug discovery, where molecular interactions are simulated, many stable logical qubits will be needed, not just a high number of noisy physical ones.
Which implies that the Jupyter benchmark, while impressive, really just highlights how much work is still ahead. It's a step, but not a sprint finish.
It's absolutely a step, and a crucial one for understanding the engineering challenges and the fundamental physics involved. But it underscores that the field is still in the early stages. The practical applications for industries are still some years away, likely requiring hundreds or thousands of stable logical qubits. The Jupyter announcement reframes the understanding of the current state of quantum computing and sets a new baseline for what a cutting-edge quantum computer can achieve today against the best classical counterparts. It forces researchers to be more precise in their claims and more rigorous in their benchmarks.
What are the incentives here? Why do these quantum computing companies continue to push for these supremacy demonstrations, even if the goalpost keeps moving? What's the value in it?
The value is multifaceted. Firstly, it's a powerful demonstration of engineering prowess. Building and operating a 50-qubit system like Jupyter is incredibly complex. It requires advancements in cryogenics, control electronics, microwave engineering, and quantum materials. Each new qubit milestone validates the underlying technology and provides critical data for improving future designs.
So it's a test of their manufacturing and operational capabilities, showing they can build bigger, more stable systems.
Exactly. Secondly, it's a crucial step for attracting talent and investment. These announcements generate significant media attention, which helps recruit top physicists and engineers and secures funding from governments and venture capitalists. In a highly competitive field, these supremacy claims serve as high-profile markers of progress. Thirdly, these experiments, even if on abstract problems, push the boundaries of theoretical understanding. They help physicists confirm or refute models of quantum mechanics at larger scales and better understand error mechanisms.
It also seems like these demonstrations serve as a kind of benchmark for the classical community. By setting a quantum challenge, they inadvertently spur innovation in classical algorithms and high-performance computing, which then closes the gap.
That's a great point. It creates a fascinating feedback loop. Quantum computing challenges classical computing, which responds by becoming more sophisticated, which in turn forces quantum computing to achieve even greater feats. This dynamic competition ultimately benefits the entire field of computation. The Jupiter benchmark is not just a statement about quantum progress, it's also a statement about the incredible resilience and adaptability of classical computing. This interplay is why the shifting goalpost metaphor is so apt.
So how does this new benchmark and the redefinition of supremacy affect the narrative around quantum computing? For a while, there was a lot of hype about its imminent arrival and disruption. Does this temper expectations or just refine them?
It absolutely refines them. It should temper the most enthusiastic, unrealistic expectations about near-term widespread disruption. It underscores that quantum computing is still very much in its foundational research and development phase. The Jupiter benchmark, by pushing the bar higher, makes it clear that achieving useful quantum advantage against an ever-improving classical baseline is a harder problem than some initial narratives suggested.
So rather than seeing it as a setback, it's more of a clarification of the actual difficulty of the endeavor. It makes the journey to fault-tolerant quantum computers seem longer, but perhaps more clearly defined.
Precisely. It brings a dose of realism. It shifts the conversation from abstract supremacy over a narrow constructed problem to the more practical goal of advantage for real-world applications. This refocus is essential for the long-term health and credibility of the field. It encourages a more critical assessment of proposed quantum algorithms and their actual benefits over classical alternatives. It pushes researchers to not just demonstrate that a quantum computer can do something unique, but why that unique capability is valuable.
Given all this, what does it mean for businesses or institutions looking to invest in quantum computing research or integrate it into their long-term strategy? Should they be more cautious now?
They should be more informed and strategic. This benchmark doesn't mean quantum computing isn't coming or won't be transformative. It means the path to get there is more complex and iterative than some might have assumed. For businesses, it reinforces the need to invest in understanding the fundamentals, exploring specific use cases, and building internal expertise, rather than expecting off-the-shelf solutions tomorrow. It's about developing a quantum-ready workforce and infrastructure, recognizing that the journey will involve continuous calibration against classical advancements.
So it's not a reason to abandon quantum computing, but a reason to be more sophisticated in its approach.
Exactly. It's about developing realistic roadmaps and appreciating the incremental progress. The Jupiter benchmark is a powerful reminder that quantum computing is a marathon, not a sprint, and the finish line itself might keep moving.
Let's summarize the key takeaways. The Jupiter 50 qubit benchmark isn't just another number. It's fundamentally reshaping how quantum computing's progress is understood.
That's right. The first key insight is that quantum supremacy is a dynamic concept, constantly being redefined by advancements in both quantum hardware and classical algorithms. It's not a static finish line, but a moving target.
And that leads to the second point, the crucial distinction between quantum supremacy, a proof of principle, and quantum advantage, which focuses on solving useful problems more efficiently than classical systems. The focus is shifting towards the latter.
A third insight is the inherent noise in current quantum systems. The 50 physical qubits in Jupiter are a technical marvel, but they are still NISQ devices, highlighting that scaling isn't just about qubit count, but about qubit quality and error correction.
And finally, this interplay creates a beneficial feedback loop. Quantum challenges spur classical innovation, which in turn raises the bar for quantum, ultimately pushing the entire field of computation forward.
So the question for listeners is, as this goalpost continues to shift, how should society measure true progress in a field as complex and potentially transformative as quantum computing?
And perhaps more importantly, what does useful really mean when discussing quantum advantage, and who gets to decide that definition?
That's all for this episode of Tech Disruptions. Join us next time as we keep exploring the technologies reshaping our world. Thanks for listening. We'll see you next time.
Stay curious out there.